Okay, should we get started?
Second.
No?
Can I ask you if we can switch this?
Yes?
Do you need to charge
No?
your laptop?
I should be okay.
Do you need to charge the laptop?
No, I should be okay.
Okay. Okay, let's try this. Sorry for that. Because I need
You need the
the
charger.
USB port.
Ah, okay.
The other speaker needs it.
Try again. One, two, three, boom. Almost.
Almost.
What happened? Why is it weird like that?
Would you like to rescale this Windows again?
Yeah. Let's try.
Okay, exactly.
No.
It's weird.
Yeah, let me see what's going on here, maybe with the display. Displays, mirror. Let's try a different resolution.
Try 1024, please. Yeah. Should be way bigger for you.
Yeah,
Better for
good.
us. All right. I appreciate it. Thank you very much.
No problem.
Thanks.
Okay. Welcome to the last tutorial, the last day of the tutorials. How's everybody doing? Okay. Make sure you go outside and look around a bit. Yeah, that's the picture if you look that way instead of looking this way. I went up the cable car this morning, it was beautiful. Projectors aren't so good, are they? We're going to be talking about, not talking about nature, we're going to be talking about Python. We're going to be talking about wrapping C code with 4 different methods in Python. Each of these have its own idiosyncrasies and tricks, things you need to know if you want to use them. So hopefully I'm going to give you a general overview of four different ways. There are many more. I'm not going to talk about PyBind 11. If I put any more into the title, I think I'd have to change the whole structure of the lecture. But we're going to talk about 4 different ways of wrapping C code with Python, CFFI, Ctypes, Cython, and CPPYY. And I'm going to sit down because it works better with my mouse, but feel free. This is a lecture that I gave a year and a half ago at a PyCon in 40 minutes. So if I added a bit more, but we've got an hour and a half. We've got a lot of time. I'm going to try and take it slow and make sure that everybody gets what's going on in the lines of code that we're going to be showing here. If you want to run it on your own, you can run it. It's an IPython notebook available at this GitHub repository on the under my name. So let's get going. My name is Matty Pikus. I'm a core PyPy developer. And since April, I've been employed full-time to work on NumPy, to improve it, to hopefully make it better. I'm working through the Berkeley Institute of Data Science in Berkeley, but I'm actually located in Israel. I'm an experienced programmer. I've been doing image processing for about 20 or 30 years. I've got a lot of experience with C, so this whole C thing comes natural to me. So if I'm going too fast or things aren't clear, tell me slow down. Feel free to raise your hand and say things aren't clear. Here's what we're going to do. We're going to take an example program. I have to sit down, it doesn't work. We're going to take a Mandelbrot fractal image, a program that creates a Mandelbrot Mandelbrot fractal image. We're going to write it once in pure Python, once in pure C, and we're going to measure the speed of execution for both of those. And then we're going to start mixing. We're going to start mixing Python and C together. We're going to talk about 4 different ways of mixing Python and C: Ctypes, CFFI, Cython, and CPPYY. They all start with a C. We're going to compare them. We're going to talk about how much boilerplate each one needs, how much maintenance, how easy it is to maintain the code that's produced, and of course speed, because that's why we're here in the first place. At the end there will be a pop quiz, and then hopefully there will be some time for questions. So let's get going. It's a notebook, so I'm going to execute the cells. The first cell here is just a lot of importing things that we need in order to be able to get going. Okay, our mission is to create a fractal image. Okay, but first we need to decide how we're actually going to represent an image, what we're going to do with it. We're going to define a simple structure that's going to be our image. It's going to have 3 fields in this class. It's going to have a width, a height, and data. Now the data is kind of tricky because we actually want to be able to index that data, and so we're going to define it as a byte array. Byte array, is that okay with people? It's like a string in memory, okay, but a string is immutable. So a byte array, we can actually change the values of it as we go. So we've got this chunk of memory that we've allocated when we initialize our class object with a bunch of memory that we can then fill in with values, and that's going to be our image. And we're going to allocate one of these images with a width of 1500, a height of 1000. So I'll go ahead and allocate that image. So now I've got an image with a big chunk of memory. How many pixels does it have? Anybody can do the math? 1.5 million. Good. I'm just trying to see if you're awake here because we want to do this all together. 1.5 million pixels, 1.5 million values from, we're going to call it, because it's a byte array, it's a byte of data, so it can hold the value between 0 and 255. Okay, how are we going to turn that thing into a fractal image? So someone told us, actually I took this demo from a lot of stuff that's been around on the internet. So we want to loop over the image, over the x and y values. At every value, at every pixel, every one of those 1.5 million positions in the picture, we're going to normalize the horizontal, the x value, from between -2 to 1. And we're going to normalize the y value. That'll run from -1 to 1 for some reason. Not really sure why they did that. And then we're going to call a function, Mandel, that will actually calculate the Mandelbrot value after a number of iterations given those 2 values, the x and the y value. X and y will actually become the real and imaginary parts of a complex number. And then we do some math on that value. That's our inner loop. So we're going to step across the image, both directions. Each position in that image we're going to be calling a C function. Now we've got some system architect. This is a bit of a construct in order to make the exercise a little more interesting. And our system architect said, we're not going to give you an input of x and y and an output of the value. We're going to give you an input of an x and a y and a pointer that's actually going to contain the value. And the return value from the function will be some kind of status. He didn't actually say which status. It makes a lot of sense in C. In Python, it's a bit awkward to handle these pointers, but we can see how it's going to, we can make it work. Okay, so since each one of the 4 frameworks we're going to be playing with has a different idea on what it means to actually create the pointer, we're going to pass it in to our outer function. We've got this outer function that's going to loop across the picture, and we're going to pass it all the way into our inner function. And then we can reuse that function in each of the frameworks more easily. And so these, just ignore this cell. It's just a placeholder that we'll come back to later. Here is our actual looping function. This is the function that's going to, if we're looking at, when I look at looped functions, I always look at the internal part first. So if we look at this line, okay, that's where the actual work is done. We're calling some function. Where's that function coming from? It's coming from the input to the outer function. It's getting a real and imaginary numbers, a number of iterations, and it's actually returning the value to be used in this one val as a pointer. And then we take one val, we dereference it to get the 0th value of it, and we shove that into the image data. Okay, so our function that's actually going to create the fractal accepts the image from before, right? Our class that has a width, a height, and a pointer to some data, accepts a number of iterations. That's for our internal function to know when it should stop trying to calculate the fractal. Accepts a function, and then as I said, we've got this little thing out here that's actually going to be something we can handle as a pointer internally. Okay, and then these other lines here are just to normalize the pixel value to be between -2 and 1 and -1 and 1 so that our function can actually do its work. Okay, questions so far? Regular Python function shouldn't be too complicated. Okay, here's the calculating function, the function that actually does the work. Calling it Mandel. Okay, it takes an x and a y, a number of max iters and a value, which is the same interface we had before. It creates a complex number from the x and y, does some math on it. If the value of if the square of the value is more than 4, then it'll set value 0 to I and return 0. And if not, it'll peek out at the max iters. It'll give us the gray parts of the images, the darker parts of the images. We didn't actually converge on a solution when we were calling this function with the x and y. Questions on the calculating functions? So all we've got is two functions. We have an outer function and an inner function. And now let's try it out. Okay? So the scrolling here is a bit awkward because I've got the image large enough so that you guys can see the whole text. Okay, so we ran this cell number 7. And we called our function create fractal with our image, with 20 iterations, with our function Mandel, and our one val. Our one val is a byte array of length 1. That's the way we can use it as a pointer. And then we set up some timers. Some timers to see how long it takes to do the function from start to end. Our pure Python time is end minus start. And it required on my computer 3.7 seconds to actually compute the fractal image. Anyone get different answers? I've got a pretty strong machine. So 7 seconds. We got anything between that? 4.5. Okay, cool. So people are successfully running the function. Now let's just make sure that we actually have a Mandelbrot image. So we'll run the next cell, which actually shows us the image. And there it is. Okay, I gave it a bit of fake color. These blue, I think the blue areas are the areas where the iterator fell out, and the yellow areas are where it came back too quickly, and the ones in between are where we got some nice data. Okay, so now we have our little toy problem. We've got it all done in Python. The next thing that we want to do is, everyone knows Python is slow. So we outsource the whole thing to a contractor, which kind of represents if you're given some C code. Okay, contractor rewrote the whole thing in C, budgeted it for 1 month, contracted for 2. We got the code after 4 months with no tests. Okay, so we now have our Mandel function in C99 compliant C, using a complex struct for our complex. And now the pointer to val makes some sense. So let's take a look at the C function, the inner function, the Mandel one. Okay, it still takes an x a y, iters, and it returns its value in this unsigned char pointer to value, to val, returns an int, okay? And the code in here is pretty much the same code we had with our Python function. Should we compare them? Let's go back up and look how the Python function looked. Okay, try to remember what's written in this line here. It's pretty much the same thing as is in our pure Python function here. Just Python's a little more compact. Real times real plus imaginary times imaginary greater than equal 4. That's pretty much what we've got here. Same thing. C real F, C real F, C imaginary F, C imaginary F, and return 0, otherwise return the max hitters. Okay? So, we may not have a full validation suite for our simple function here, but what we did get was a function that, that does our loop. Okay, create fractal. If we look at it from the inside out, from this line here, this function doesn't accept a function as an argument, but it does accept an image and a number of iters. It does the same manipulations with the iters that we did before, with the pixel value, the x and y, and calls our function Mandel in order to calculate the Mandelbrot image. Okay? Now this next line, people who are working on Windows, the next cell, I'm sorry, people who are working on Windows, hopefully it'll work for them if they have a compiler installed. How many people here are on Windows? Ah, only a few. Good. So look at your neighbor if it doesn't work for you. This actually compiles using GCC, which is not what you want to do. You're going to have to change it to compile with whatever compiler you've got. And then I've got a little bit of boilerplate code here to save the image and to read an image from a file that the C code saves. And we can see that the two implementations are pretty much the same, except for one important thing. The pure C code runs a lot faster than the Python code. Okay? Questions up to here? Up to here, we're just kind of setting the stage for the whole tutorial. We've got our two ends of the spectrum. We've got code that runs in pure C, finishes in about 130 milliseconds on my computer, maybe up to 400 or 500 on some older machines. And in pure Python, 3 seconds. So it's about 26 times faster, 25 times faster to run in C than in Python. Okay, so let's talk about Ctypes. So what we have so far is we've got a function called, we've got a SO, we've got a shared object or a DLL called lib, don't do double clicks, that's called libcreateFractalSO. If we look on the disk, we'll actually see that there. That's a DLL with our function inside of it. So that's much like any other C code that you're going to get from somebody who gives you C code. You're not actually going to work with the C itself, although you could. There are other modes for working with some of these libraries that might make that even a little bit faster. But we're going to assume that you've taken that C code, wrapped it up into a DLL or a shared object, and you've been told you need to work with that. Okay? Now, why can't we use the C function wrapper that our contractor gave us? Because we want this to be part of a pipeline. We want to be able to call this function with our image, then continue on in Python using that image or using something else and doing another step in a pipeline of operations. So it's inconvenient to have to call out to C with subprocess or something else to actually get it to run the executable file, save the output to disk or to somewhere else or stream it to us, and then to pull it back in. So what we want to do is use the shared object, the function in the shared object, as our target, and wrap that function with some Python code so that we can call all this shared object from Python. Okay, so we've heard about some methods to call from C to Python. The first one we're going to look at is one that's included in the standard library. It's called Ctypes. Ctypes, actually all four of these methods, all four of these different ways of calling out to C have their own little mini language. Okay, for some of them the mini language is more exposed than others, but each of them have this like language that they've developed that translates between something that looks like C to something that looks like Python. When I look at Ctypes, I think of it as a way of writing Python in C. Okay, we've got all these Pythonic things. The first thing we need to do is to define our image structure. So instead of in C or in Python where we simply have attributes of a class or a structure, here we've got a class that inherits from C-type structure, and it has fields. Okay, it has 3 fields, the width, height, and data, much like what we had in the 3 fields in the pure Python version. So the width is a C-types C-int, which again is a C-types specific definition of an integer that can work both in Python and in C. Height is also an integer, and data is a pointer. It's a C-types pointer to a C-types CUint 8. Okay? And when we actually call the init of this class, it's a Python. What happened here to my? There we go. When we call the init to this class, we're going to actually allocate an array cache of data so that we can hang on to it, because we need somehow to hang on to this block of memory we're allocating. Okay, we've allocated a block of memory, but here in the Ctypes structure, we have no place to actually hang that block of data. So we've got to attach it here somehow to the class. Okay? So we have something we're calling the array cache, which is going to be a cache of blocks of pixels that we're holding off to the side. Okay, so there's this whole problem with pointers and keeping the pointer alive, okay, keeping the data alive. What do you do in C when you want to allocate a pointer? When you allocate a block of data? What's one of the major problems with C, right, is that you do this malloc thing, or this new, or some kind of other alloc operation, and now you've got something that you've allocated. Now you're responsible for the lifetime of that block of data. Once you've called malloc, you're also responsible for calling free to get rid of it. Okay, so in C, you have the responsibility to manage the lifetime of chunks of data that you've allocated, as opposed to Python, where it all just kind of happens for you. Or C++ also, when you do a new class, it kind of handles it all for you. There's a garbage collector in there that goes through and manages the lifetime of objects. So here we're actually going to manage the lifetime of the object ourselves. We're going to cheat a bit, okay? Because what's missing here? We've got the fact that we're allocating it here. We're allocating this chunk of data, but what don't we have anywhere? Nowhere in the code that I've shown here do we actually free that thing up. Do we actually get rid of it? Okay, so every time we allocate an image, every time we build an image, we're allocating another chunk of memory for the data, and we're never actually cleaning it up. Okay? So if we want to clean it up, we have to actually think about how we're going to manage the lifetime of this image and to be able to clean up that data. One of the issues with Ctypes, with the whole interfacing with C. So we've got a little trick here. If we don't have a piece of memory that's the right size in our array cache, we're going to allocate a chunk of memory, and we're going to set the data to actually that pointer. Now, how does this work? When I do Ctypes CUint 8 times something, I've created a class, I've created a class object that can allocate a chunk of data. All right, that's this Ctypes uint8 times width times height. Let's see how that works. Let's put in a cell here below this. We'll run this first of all so that we'll have everything we need. And now we'll say A equals Ctypes C uint8 times 100. And print A. Okay, A is a class. It's not an object, it's the class itself. We haven't actually allocated the memory. We're just saying we've got an object that can hold this, that will allocate this much memory when we ask it to do so. So if I go back up here and I say B, actually allocate me one of these. Okay, now B is an actual 100-byte array that's been allocated. It's a chunk of memory that's been allocated. As long as B is alive, that memory will stay alive. So that's what happens here when we've got our, when we do our, here it is, self data equals self array, array cache. So we're actually going back into that cache of classes that we've built for ourselves and allocating one of the members of that class to create the data. So now the data is actually attached to our new class object. And once that class object goes out of scope for Python, that object will be collected. So that's how the garbage collection works in Ctypes. If we attach a chunk of memory to a Ctypes object, once that object goes out of scope, the memory will be collected. Okay, one more thing I need is a memory view of the data in order to be able to save it to disk. I want to save it to disk as a NumPy array. NumPy arrays work really well with memory views. So I'm going to add a helper function into this class that's going to create a memory view of the data. Okay, and it does it in a very inefficient way. It creates another chunk of data. Okay, this is another chunk of data that's not the class data itself. It's actually just another piece of data, and I copy the data into it. Okay, so any questions up to here about this structure? Yeah, go ahead.
Why you decided to put the cache as not as an object field, but as a class field? So why is the cache shared between?
The cache isn't shared. One of the first things that I did in Python was actually this type of allocator. And what happened was I made a new class every time I called an init. Okay, but I don't want to do that because that'll make hundreds or thousands. If I have 10,000 images that I'm going to work with, I don't want to create a new class each time. Okay, we said that this line here creates a class. I don't want to create a new class object, class type, each time I call my init, because then I'll have thousands of these class definitions just sitting around eating up my memory. So by caching them in this array cache dictionary, I can only create one for each size of image that I create.
It's a class, not an object.
It's a class. What self-array class is holding is the classes, and in order to actually allocate them, I have to put the parentheses at the end. Okay, there was another question over here. Same thing? More or less. Don't be afraid to ask. We've got time here. The point of this tutorial is to make sure that you guys come out with the working understanding of how to use these things. Yeah. Yeah.
There are the variables width and height, and where are they defined in the scope? Why is it not start that width and start that height?
Yeah, they probably should be. They probably should be. Good point. I wonder if I actually use it in the code and if it passes. And if not, I don't know how. Okay, so we'll see later on if I actually use that. I think maybe in the current version of this notebook, I don't use this function anymore. Not so good. Very confusing for a tutorial. Yes?
I mean, so you've developed this kind of NumPy-like array structure. Is there a way of working with Ctypes with a NumPy array itself? Or do you have to create kind of like this
No.
pointer class?
Yes.
Okay.
But you could actually make, if you know what size your image is ahead of time, you could, rather than have this data be a pointer, you could have it be that class itself. Okay? So I purposefully put this in because otherwise Ctypes looks really easy. But it gets complicated when you get these pointers and blocks of memories and classes. So it's meant to be complicated and confusing. Yeah.
Please don't offend anyone. Very simple question, but I really want to get why did you return a memory view of the copy of the data instead of returning a memory view of the data itself?
Good question. I think I tried returning just a memory view of the data and it didn't really work out. But let's see if that works. So there's nothing like having a notebook, and that's the whole reason we do things in Notebook, is that we can then try them. What happens if I try to print memory view of B? Okay, because B is basically the same thing as the data, and I'm missing something, missing a parentheses. Thank you. Yeah, that works. So that would have been a much easier way to do this.
But then put the reference in the
Yeah. So then, as someone pointed out, it would be a reference. It wouldn't be as soon as that data changed under my feet, the memory view would also change because the memory view is not a copy. It's a view into the data. So this is a way of actually copying the data out and creating a separate copy. I don't know if that was my point, but I'm not sure deep copy works with Ctypes. It's a question. Something worth looking up on Stack Overflow. I don't want to go into that right now, but that is a question that we could ponder. Okay, more questions about this whole memory block allocation thing. These are good questions. Keep them coming. Sign that people are actually trying these things and thinking about them. There's no stupid questions. Okay.
Actually, I have a problem, but related. I could not compile the main file.
You couldn't compile the main. Are you on?
3 different compilers.
Okay.
There is something to do.
Did anyone else have a problem compiling? Ah, okay.
This is a good time, I think.
Maybe I'm missing a header here in my file.
I don't think so. Maybe I'm missing something in my installation.
Let's see. Yeah, let's see what I did here. So mine, I think I compiled. No, I didn't compile it here. Where did I actually compile it? This is the C file. Where did I actually compile it here? Ah, I didn't actually compile it. Okay, let's see what happens if I put it into a terminal. And we'll try compiling.
I mean, just compiling, not even the linking to it.
Is that what you all know?
Okay.
And so I also need to add the other great fractal C. and the other one. Yeah, for me it works. Okay, and if you want to do it, if you want to create the shared object, I think you need the create fractal C and the Mandel C, and you have to use shared. Yeah, so I just compiled that right now. Okay, what error are you getting?
I think it just doesn't see the time.
Time.h?
It doesn't give me an error at the include line, but just doesn't see the functions in Cyclone.
It's not exposing anything.
Yes,
Ah,
because I don't see what process CPU time ID or.
and M lib create. Yeah, I've got the correct create fractal function here. Did anyone successfully compile it? Okay, interesting. What are you on, a Mac or Linux? Mac. Ah, we may have reached the issue here. How many people here have Macs? And did you successfully compile it? No? And so what version of Mac OS do you have? And
I mean, everything else compiles in just the main.
yeah, just the main.
Yeah, just the main. Compile with -c, really just compiling. Not meaning no linking, just the compiling.
I mean a C, sorry. I don't know. What line is it choking on? Does it give an error?
All of them where there is something that should come from time.
I wonder if it's Clang.
I tried playing it, but it's easy C, I tried G++.
Yeah, that works too.
So, okay.
Sorry,
Some update was the first line header file.
I don't know.
Okay, then, thank you.
I'm sorry. That's so frustrating. I mean, okay, so where were we? We had finished the Ctypes. Okay, so we finished discussing all the different structure, this class of the Ctypes image. We create a instance of the Ctype of that image, okay, by calling the class function. This is how we load the DLL into, or the shared object into Python. We call Ctypes CDLL load library. Now we have a handle to the DLL, to the shared object. Okay, we've opened up the shared object, this lib create fractal SO. We've opened it up, and now we have a pointer to it, or something that Ctypes can fish the functions out of. Okay, remember that DLL has that function in there somehow. We've got to convince Ctypes to go into that shared object and find us the pointer to the function. That's this line. Okay? Ctypes, we're telling Ctypes, look, inside of that DLL, inside of that shared object, there's a function called create fractal. That's that function that does the weird things with the complex numbers. Give us a pointer to that function. And then the next step is we could call that, okay? I could now empty out this cell, and I can ask what is create fractal Ctypes. It's a function pointer object. It has a call method, so I can put parentheses on the end of it and call it. No one will protect me, okay? This is the easiest way to create a segmentation violation with Python and with the C code is to call a function the wrong way with the wrong arguments, things it didn't expect. So we have to somehow tell Python or tell Ctypes, please protect me. I know what the signature of this function is. I'm now going to tell you how to call that function so that every time you call it, protect me, make sure the arguments are correct before you feed them into the C function. So that's what this thing is here about this argtypes. It's saying that function gets called with a Ctypes image and an int. Okay, the create fractal function itself. The Mandelbrot Ctypes function gets called with a float, another float, an int, and a pointer to a uint 8. Okay, so every function, when you pull a function out of a shared object and you want to use it, you've got to tell the Ctypes what you're going to be doing with that function. Otherwise, you could get yourself into a lot of trouble.
So this is not a compulsory step, but protective from.
Yes. Yes, you don't have to do this, argtypes. There's also a res type, I ignored that. But the argtypes protects you so that when you call the function, Ctypes will check that what you're giving to the, it knows how to convert what you're giving to the function into those specific types. Okay.
It would be faster without this.
Maybe. And notice what it did. I tried calling the function without giving it what it needed, and it yelled at me. It says the function takes at least 2 arguments. If I give it the wrong arguments, it'll say you gave it the wrong arguments. But this all happens on the Python level before it gets into calling out to the C function. Okay, this isn't the C protecting me. This is the framework, the Ctypes framework protecting me. Okay. Now we're going to do a little bit of timing. We're going to call this function twice. Once we're going to call the external function that basically will call C to call the external function in C. Within that function in C, it'll iterate over 1.5 million times, calling the internal C function. Okay? And then the next time, we're going to write the loop ourselves. That loop function that we had at the very beginning, we're going to call that loop function, and internally we're going to be giving it the C function to call 1.5 million times. Clear what the difference is between these two calls? One, we're using the C function to call 1.5 million times. Once we're using the Python function to call 1.5 million times. So let's see how the timing goes. Okay, we got a little better. All right, do you want me to go back up to this, this was the Ctypes 1 call. Okay, that's when I used the create fractal Ctypes, which is what I called that function here. That's the external function that I'm calling from here. And the other time that I do the timers, this whole bit here, I'm using this Ctypes, the create fractal function that we had up in one of the first cells. Okay? So this is a Python function calling 1.5 million times over the loop using the Mandel's Ctype function to actually do the work. I had to allocate some kind of value that Ctypes wanted to work with. And that's about all that was tricky here. Okay, so calling the external function from C was 132 milliseconds. Using the internal function, only the internal function, was 1.5 seconds on my computer. Okay, and just to prove that it worked, I save those images to disk. I can load them from the disk. We see that the images worked. Both of them come out pretty nice.
To compare it with the pure Python, it was 3,000.
Right. We'll do that at the end. We'll compare all 4 of them when we get to the end, but it's a perfect question because I have a slide on that. Okay, next. Next. What happened here? Getting confused with title. Here it is. CFFI. Who here has heard about CFFI? Tried it? Played with it? Good. Handful. CFFI was written, came out of maybe 5 years ago or so as a replacement for Ctypes. If Ctypes is writing C in Python in C, then CFFI is writing C in Python. Okay? It's the approach of, instead of doing all these things around to actually protect ourselves from C, why don't we use C as directly as possible and use the compilers and headers and things that actually already exist in C in order to let Python know how to call the functions automatically. So we've got a lot. What we're doing here is we've created we import CFFI, and then we create something to hold all the state. Okay, we need some kind of object to hold state of whatever we're going to build. So we create this object here that's called a FFI object. And then there's two stages. In this way that we're using CFFI, there's different ways to use CFFI. The guy who created it doesn't like this method so much, but this is a quick and dirty way to get some kind of Ctypes compatibility. It's a little bit slower than a more complicated way of actually calling CFFI. The advantage here is that you don't need a compiler. Once we've compiled our shared object, whoever succeeded in compiling, sorry about that, was succeeded and has a shared object, or you got it from someone else. Maybe actually you could copy with a discount key from someone else if you want to actually do the tutorials. But CFFI in this mode of operation doesn't require a compiler. What it does require is the header. It requires the header in a very specific format. Okay? We need the header file. We open up this header file itself. All it's got in the header file is a type def of the image structure written in C, okay, because it's a header file, and the declarations of the two functions. That's the contents of the header file. Okay, we take that header file, we read it in. What CFFI cannot do is it can't handle all kinds of preprocessor macros. Things like include, okay, it can't handle that. So if you've got include stdio in your header file, you've got to somehow clean that out before you give it to CFFI. Or if you have macros like if def gcc, else if def win32, else if def clang, whatever clang has, CFFI can't handle all those. It only handles the actual C code definitions. There are a few small exceptions to that, but they're not worth going at the first stage. You need to have clean, pure C header in order to use CFFI. Okay, and what we do is this. We give it the text of the header file, and we say, here are all the definitions, all the C definitions that I want you to use. Okay, we give it to this FFI class object that actually is going to hold the state of our calls to the DLL, to the shared object. And then just as we do with Ctypes, we call DL open. Okay? But the minute we do this DL open thing, CFFI already knows, because we gave it the declarations of the functions, what the input types are, the output types are. We don't have to do the arg type and all those other dances. It also knows how to allocate a class like this C image. We'll see how we do it in a second. Okay? This is CFFI. So we did that. In order to create the image itself, that's the first line of the next cell. The FFI has the state. It knows if we tell it, make us a new C image, C, little c, big image, make us one of those. It knows how to allocate the memory that it required to do that. That allocated memory, it's a new, is in this object called the image, img. Okay? That memory will stay alive as long as image stays alive. If image goes away, that memory will go away. So when we call FFI new, we have to make sure that we're hanging on to whatever we've created. All right, the same thing with the data. This is why I create an instance variable here of data1. Okay, this. That's the size of the image. Yeah.
Why do you use that? Isn't the pointer already kept by image.data?
Perfect question. Because it's exactly what I wanted someone to bring up, and the answer is no. Image data is a pointer to, is just like C. That's why I said CFFI is like writing C, but in Python. That's a pointer. And just like in C, when you can take pointers and you can point them all around at all kinds of different things, that's not a replacement for actually hanging on to a chunk of memory. It doesn't manage the memory for you. Okay?
So all the pointers you have here are like non-owning. They never.
The pointers don't own the data. Exactly. Very good way of putting it. So image 0 data does not own data 1. Data 1 has its own lifetime. A very common bug with CFFI is that data 1 goes out of scope. Image 0 doesn't go out of scope. And boom, you've got a segmentation violation because you have memory that's been freed and you still have a pointer to it hanging around and you might be using it. Okay? So if you get a crash when you're using CFFI, the first thing to think about is where did you allocate memory and then forget to hang on to it. Okay, so from here, this is the complicated part. All right? This is basically the exact same thing that we did above. We use the DLL, we use the function in the DLL to create the entire fractal all in one go. And then we call again into C, we call again with Python, iterating through our image 1.5 million times. And then we save it and we do some timers around it. And okay, any questions about this block of code? These 6, however many lines there are, is the important part. This is actually how you use CFFI in this mode. Okay, so up 130 milliseconds to call the external function and 640 milliseconds to call the internal function. Okay, we're getting closer. We're doing better. And let's just make sure that we got something that's valid. Looks pretty good. We got our 2 fractal images. Still doing okay. Questions about CFFI? All right. Next, Cython. Who has used Cython? Yeah.
Sorry, can I still ask you a question?
Yeah, still.
So,
Yeah.
you know how you say you have to hang on to the memory as well as the pointer?
Yeah.
Does that basically mean that you have to make sure that not only you forget what the address of the pointer is, but also like the memory, like you don't overwrite it or something?
Well, data 1 will be a pointer to that memory.
Yeah.
Okay, so you can access it either through image 0 data or through data 1, because they both point to the same thing.
Yeah.
So I think, did that answer your question?
So does data 1 own the data?
Yeah, data 1 would own the data, but image 0.data is actually pointing to the same data memory.
Yeah. Okay.
Okay? Yeah.
Can I take away ownership from this? Like, can I say like, Python, don't delete this, C will delete it if you pass it to it?
There is a way to tell when you do new, you can actually tell, you can give a method to CFFI to do some garbage collection with. That's an advanced topic though, and we won't cover it today, but there is a way to do it. The documentation of CFFI is pretty good if you know what you're looking for. So you kind of have to know how to read it in order to read it, but the answers are there. And yeah, mostly. Kind of like C-types, the C-types as well. I found that like I have to know what the answer before I can actually understand the question in some of the Stack Overflow answers. Okay, moving on to Cython. Who has used Cython? Okay, I've used it too. Great, about half the people. It's pretty magical, it's wonderful. We can even use it from the Jupyter Notebook. If we do this load extension, I'm pointing at my screen. That's going to help you guys a lot, isn't it? If we load this extension Cython thing, that'll let us use Cython from the Jupyter Notebook. And here's how we do it. Cython is also it's got its own little language, mini language that we have to learn. It's kind of a mix between C and Python together. Okay, when we have these CDEF things that look kind of like C, but we also have these dots at the end and things that look like Python, the colons at the end that look like Python. So here's what we do. We have this is actually the text that we feed into Cython. And Cython then takes that text and just as Python itself does, interprets it and does all kinds of magic with it. And will actually create a shared object, a new shared object that wraps this all up. It'll actually create a Python C extension module out of all this. Okay, so there's a compiler there somewhere that's lurking underneath. The compiler is fed code that Cython mashes together, creates some kind of C out of all this. Okay, when we do this, what we get back, who's seen this yellow, can I do this? Yeah. Who's seen this kind of output that Cython creates? Oh, good. Okay. So I'll go over it a little bit quickly. What happens is Cython creates all this, and then it goes back and it says, well, how much code did I create for each line in the original file? And that's what's hiding underneath these little plus things, is the number of lines of code that it's creating behind each of these lines. So this actually turned into one line of C. That's why there's no yellow. But this turned into a whole bunch of C. Okay, that kind of hurts the eyes to look at. I'm glad that it's yellow. Okay, it created all that for that one line of Cython code. All right, but we don't really care because it did it all for us. If you're really trying to tweak the performance, you want as many lines as possible to be white and and light yellow as possible. Okay, so this would be a case where you'd probably want to tell it something about this pi image and these iters so that you can get rid of some of these lines. Tell it that iters is an int or a float or whatever it is. That'll already get rid of a bunch of it. And if you can actually describe the pi image in some way to Cython, then you can also save a lot of extra boilerplate code. Okay, so we've gone ahead and, sorry, I didn't actually go over what I did here. So again, we've defined some kind of a struct in Cython that has a width, height, and a pointer to some data. That looks pretty straightforward. We've got a function, create fractal and Mandel, the two functions that we brought out of our C. That's why they're all under this block that says these guys all live within the createFractal.h. Okay? This struct and these two functions, they live inside of this createFractal.h. CDEF extern. These are the things we're going to pull out of that header file. this is our function to create the, let's do this function first, it's a lot easier. cpdef means this is a mixture of C and Python. We're defining a function that returns an int, and it accepts a float, real, float, iters, char with contiguous data called value. Okay, that's why when we then created this function, and we look at cpdef mandel, it actually has less code than it did when I first did it, and I didn't define all those, didn't give, let's see, declarations to all the arguments in the C function name. Okay, create fractal. This we just use as a regular C function, as a Python function. Okay, we're doing, don't click it. It doesn't have a cpdef, it has a def. That's why I don't have to give these arguments, I don't have to give these arguments declarations. But it does internally have an image and an iters, and it allocates this data, which it takes from the Pi image. Stop clicking. Okay, and then this is our actual function. Internally, we're just calling into the C function that we got from the DLL, from the shared object. Okay, questions about the Cython code? I admit I'm not as much of a Cython spec as I am with CFFI and Ctypes, but I hope it's clear. Okay, so let's go ahead and use this guy. Same thing as we did before. We're going to make one call using the Cython create fractal image, and we're going to make 1.5 million calls using the create fractal function, and there it is. Okay, 133 milliseconds for the single call and 600 milliseconds for the multiple calls, and oops, and we'll go and doing something right, or else we're cheating. Okay, maybe I'm cheating, maybe I'm just reading the same files each time. All right, one last one. We've got another 25 minutes, and then hopefully we'll have time for a pop quiz yet when we finish CPPYY and some questions. CPPYY, what happens if what you've got to call is not C code, rather it's C++ code? Okay, traditionally that's been a real problem for any kind of wrapping system, whether it be Perl or any other language that you want to wrap C++ code with. Even if you want to wrap it to call it from C, you have to do all kinds of manipulations in order to get it to work. Llvm, which is a compiler suite that kind of there's a whole GCC world and there's the LLVM world. LLVM is lower level something that takes C code or C++ code or something, funnels it all down into some kind of internal representation, and then LLVM is what actually turns that code into assembler. Okay, so it's like you can look at it as a kind of a compiler funnel. It'll take C# code or C++ or any kind of code and turn it into this internal representation, and then LLVM takes that internal representation and puts it into actual machine code. Okay, so that LLVM machine, we can use it to take some kind of representation that of the C++ wrappers that we want to use and make new wrappers as a shared object, much like Cython does. From last week, you can call pip install cppyy, regular PyPI repository of packages. It's a young package, it's still growing. PyBind 11 becoming really popular. Personally, I don't like it for reasons I'll talk about when we talk about the pop. LLVM as well. But from the same out debug information. CFFI, because it has the same kind of life as CFFI saves its own state within itself. We tell it, this is the header file, and this is the SO that we want to be able to use. And then we have to define a C++ class from the C struct in order to manage the memory. Okay, because we're already in the world of C++ here, now we can do the memory management via C++ statements. C++ is a garbage collected language, so we can use C++ semantics to actually manage the memory of the image that we wish to allocate and free. Okay? People fluent with C++ will be able to read these lines of code. That inherits publicly. It has a constructor. The constructor is what's equivalent to the init function. That actually goes ahead new by height in size. Okay, so this is a function. That's a function, or something like a function. With the initializers, let's say through the initializer of the class, and that's the function body itself is empty. This is the destructor. Okay, it deletes the data. That's a constructor. Is that right? Yeah, that's a copy constructor. And that's a equality operator. If we assign one CPP image to another, it'll actually do with an equal operator, it'll call into this function. So this is all C++ magic to define the classes. Okay? And that's pretty much it. We do need a function. Why did we create Fractal here? Basically, this is just a copy of the function from above. This is our global create Fractal once from the DLL. Once requires 38 milliseconds in calling, and it actually works. There it is. There's our fractal. Okay, now let's get to the heart of the matter. Let's compare all four of these. We've got a point where we can, any questions about to compile your code. Susceptibility to bugs. Okay, all of these have a mini language. There's no way around getting your head. You have to wrap around not only C and Python, but some kind of, now it gets Cython and Ctypes, and why you can use C++ const. Productivity. Cython functions, you can run NumPy code in because what's PyPy back to Python and see what's going on inside, and also in order to translate from whatever structure PyPy has inside of it to something that can talk to C is expensive as well. So if you're using a lot of NumPy or TensorFlow or a lot of other C extension in your code, and that's where your performance is, then you should stick with CPython. PyPy is not quite there yet with making that stuff fast. it works, but again, pandas is a lot of C code inside of it, a lot of Cython generated code. All those things you saw in yellow will be slow in Python, in PyPy. Yeah?
How about number?
Numba, I didn't actually try it. Numba should do pretty well with this exercise. I think there was another tutorial about Numba, but yeah, they do really well with loops. So yeah, Numba's a good kind of compromise if your code is mainly numeric. Right? What Numba does really well is taking the numeric code and jitting it down to something that's fast. If things are more complicated Python code, like having to do with strings or having to do with other generator functions, then Numba will have a harder time. But Numba's a great project too. More questions? Keep it going. Yeah.
So suppose you had like a bit of code which you would want to run in PyPy. How do you interface with that?
Can you embed PyPy in Python? No. No.
Like as we did here with like C, Cyclone and those things.
No. There was a couple of projects to kind of pipe stuff in between the two, like set up some kind of a streaming. So you've got an executable here of PyPy and you've got an executable here of Python, and you make them talk to each other. I don't know. What do you think? Will they work someday?
Probably not.
Yeah. So yeah.
It's just easier to run everything in PyPy.
Right. There's not really a reason these days not to try PyPy, other than you lose maybe 10 minutes of like switching your virtual environment around. But I'd say give it a shot. Might help. More questions? Questions about the actual topic of the PyPy thing was just like my, but questions about Ctypes and CFFI and yeah.
So the CFFI is using this Llvm?
Yes.
Which can compile a lot of different languages from what I understand about it, right? Is there any, will they be support for other languages throughout this interface at Llvm?
CPPYY is specific for C++. It's using this generic LLVM in order to do its work. There are a lot of other Python projects around LLVM that try and to leverage that support for LLVM in other ways for other things, other languages. Yeah.
How does CFFI handle ownership? Because in C++ you often have the pointer and you don't know do I have ownership or not. And if you're lucky, this is written in the comment above. But I know from Byte Array that this is one of the main challenges to handle.
Yeah, so if it's a challenge in PyBind 11, it'll be a challenge for CPPYY. There's no real magic silver bullet there to handle object lifetimes. It's one of the more complicated things in computer programming, although it doesn't make the list of the top 3, right? But yeah. It makes it easy to be able to write the code to actually come back. It makes it easy to write the code in order to handle it in C++. So if you know C++ and you know how to manage those object lifetimes, you can leverage that knowledge in CPPYY just as you can in PyBind 11, but it does require that knowledge. Yeah?
So in the Ctypes, you have in the class you have a as memory view function.
Yeah, I don't think I ever actually used that in there, did I?
So, well, I was wondering about it because kind of like a pointer, but it seems to also keep the object in scope. Is that right?
I think that was the idea. I kind of forgot what I did there. I did it a year ago, but the idea of memory views is a very powerful one. It was kind of an attempt by Python to make NumPy, as far as they were willing to go, to put NumPy into the standard library. They said, okay, we'll make this generic thing that's called a buffer. Any object that's got some memory attached to it will be able to make this memory view of it. It'll be a standardized way of handling things across different languages and across different C extensions, and pandas can make a memory view and NumPy can make a memory view, and then you've got this thing that's a memory view that has some standard description of what it contains and a standard way of managing its lifetime and its memory. It didn't really take off all that well, but it's still a good way if you have a distributed system and you want to distribute your some pieces of your object around. Memory views are a nice way to do it. More? Yeah.
If I'm not mistaken, there is still some difficulty in Ctypes and CFFI, and I want to wrap some C99 code that takes double complex or value or returns some double complex value, which there is some issue with wrapping C99 complex types.
I don't know. Are there open issues on the bug trackers about them? I think there might be something about complex and Ctypes. I'm not so aware of CFFI, but maybe. Yeah, I don't know. You have to check in the issue tracker. Some of these things get a little hairy because both of them, at least in the mode that we looked at, they use something called libFFI underneath to actually do the work. And so if libFFI has bugs in it that relate to these, then both CFFI and Ctypes will have some problems there dealing with those things. And I think libFFI, CPython doesn't update it ever. Like they basically depend on some really ancient version of libFFI, and CFFI updates every now and then. Yeah.
A few months ago, I saw that perhaps in LibFFI, these C99 complex blocks were already eliminated.
So yeah, so maybe it's fixed.
Yeah,
I don't know.
I hope CFFI will catch up.
Yeah. If there's an open issue, then it should be okay. I mean, someone will close it eventually. More questions? We have 2 more minutes. Yeah. About PyBind 11? I didn't say anything. So PyBind 11 creates, just like Cython does, all this crazy C API stuff that's very tuned for CPython. But if you try and use it in PyPy, it kind of, the JIT goes crazy. It doesn't know what to do with it. It's got to be handling these objects back and forth across the C to Python border all the time, and really ruins the JIT. Whereas CPPYY and CFFI are both very compliant with PyPy. They will be fast, even though you're crossing the border, even though you're crossing over into C land and coming back. Both of them will be very, very quick. So if you're thinking about using PyPy, you should think about using CPPYY and CFFI rather than Cython, PyBind 11, and Ctypes. Thank you very much. I hope it was productive.